Okay. Proof by induction is a paper 1 topic. It usually comes up as a short question, which is 30 marks, which is also known as section A. And this topic normally comes up as a part A or part B of a short question, and then depending on the proof that they want you to prove, it's usually between 5 and 15 marks for that part A or part B of your short question. Okay, so there's just a few things that we have to get into before we get into the actual proofs. So a note, first of all, is from our probability in paper 2 actually, is n factorial, which is n times n minus 1 times n minus 2 ... times 3 times 2 times 1, where n is an element of natural numbers, or n. So that was just our factorial that we had from paper 2, and we're going to use that then later on in our proofs. So what we'll start with first is summations. So summations basically is when we're trying to gather up every piece in one go. So it's kind of a bit like when we go back to sequences and series and we're trying to find the sum of all of the numbers together. So we're kind of using summations in that way, along with this chapter. So what we'll have is this new symbol called sigma, and we'll just stick an n on the top and we'll say r is equal to 1, 3r equals, and we'll just write this out and I'll explain what this is in a second. Equals 9 plus ... Okay, so this is what our summation would be. So sigma, which is our new symbol, stands for the sum. So sigma is the sum. Then we've got r then, which is how many numbers you want to go through. So it goes through all natural numbers from 1 to n. Okay, and this won't make sense until we do an example of it. So we'll do an example. Evaluate sigma 8r is equal to 1 r to the power 4. Okay, so what that means is that your 8 is the number of natural numbers that you want to use in your question. So in your question, so for example, when we go back to here, n was up the top, whereas in this one we've got 8. So 8 is the number of natural numbers in our question. Because we don't know the amount of natural numbers here, that's why we have to continue on to 3 times n, whereas we know what the natural, or what n is now, so we can only go up to the number 8. Okay, r is equal to 1 then, so this is the number that we want to start with. So number that we start with. So for example, up here we have 3 times r, whereas in our new question we've r to the power 4. So wherever you see r, we're starting with the number 1, so we're filling in 1 for r in this question, and then we keep going all the way up to the number n. So we don't know what n is in this question, whereas here we're going up to 8. 4 then is the power for each number up to 8 in this part. Okay, so if we were to actually write it out, we'd have sigma of 8, r is equal to 1, r to the power 4. So 1 is our first one, so 1 to the power 4 plus 2 to the power 4 plus 3 to the power 4 plus 4 to the power 4 plus 5 to the power 4 plus 6 to the power 4 plus 7 to the power 4 plus 8 to the power 4. Because 8 is on top, 8 is going to be our last number for this summation, or the sum of all these numbers. So then we just put that in our calculator then. So sigma 8 when r is 1 to the r to the power 4. When we put all that in there, we get 8,772. Okay, so it's using this part here. If you were to have this r to the power 4, starting with the number 1 and going up to the number 8, what's the sum of that series? Okay, so that's it laid out for you, and then this is our number here at the end. Okay, so here's just a definition that we need to learn off about axioms. So we kind of should know this from the junior cert. It's one of those definitions from the junior cert, but if you can't remember, it's here anyway. So axioms are mathematical statements that are accepted as true from the start, and they do not need to be proved. Okay, so some things in maths we just know. Sometimes we don't know why we know them. We just know that they're true, and we don't have to explain why or prove why. Whereas other things, then we have to prove why that is the case, using theorems and proofs. Okay, so for proof by induction, here there's 3 types. So what a proof by induction is a method of proof to establish a statement that is true for natural numbers. So they might ask you what is a proof by induction, which is this definition here, and then they might ask you then to prove by induction the following. Okay, so we got 3 types of proofs that we'll go through. The first one is proofs involving series, second proofs involving divisibility, and then the third, which is proofs involving inequalities. So they'll only ask one of them. They're not going to ask more than one, but we have to know every single one of those. It's a lovely question to get. If you have it, you're guaranteed 550 marks, depending on what the rest of the question is and what they want. So it'd definitely be a nice one to have. Okay, so this is our first type. So this is proofs involving series. So the question would look like a bit like this. Proof by induction. So that's our keyword there, induction. They'll always say induction. For all n element of n. So for all numbers that you fill in for n, and they're an element of the natural number, is the series 4 plus 8 plus 12 plus ... So all the numbers in here, plus 4n being your last number, is equal to 2n bracket n plus 1. Okay, so that's what we want to prove by induction. So the first thing we want to do is to prove. So we'll have p bracket n. So that's not the probability of n, that would be proposition of case n, or the amount of whatever n value you want. So because we're paper 1, this p stands for proposition. So it's the proposition of n, or they say case n, but case n we wouldn't use. So we'll say proposition of n. So we'll say Pn, or the proposition of n, is 4 plus 8 plus 12 plus ... plus 4n equals 2n bracket n plus 1. So that's what we want to prove, and it's for all n element of n. Okay, so just repeating the question down here, okay, with our proposition n. So our proof then is that we'll go with step 1, and what we're going to do is show that the proposition when n is 1 is true. Okay, so show that the proposition when n is 1 is true, or we could write it as what we said there, the proposition is true for n is equal to 1. Okay, so you can write it this way, or you can say the proposition is true for n is 1. If you want to write both, that's fine, but one or the other is fine. Okay, and what we'll do is we're going to take the last part here on the left, 4n, and we're going to take all the right hand side, and wherever you see n, we're going to fill in our number 1. So we've got 4 times 1 equals 2 bracket 1 plus 1. So we 4 equals 2 times 2, 4 is equal to 4. So that's what we want. So we want the left hand side equal to the right hand side, and we know then that P1, or the proposition of 1 for n is equal to 1 is true. So that's our first step for the proof by induction, okay? So if you can get as far as here, you're doing really well. You could get 5, 10 marks out of 15, okay? Even if you haven't a clue what's going on after that, that's perfect start, okay? So 2 then is our assumption part. So we've shown something's true. We're going to now assume something is true and use that assumption to prove the rest of our proof by induction. Okay, so by assuming something is true, we can then show that it is true, unlike our proof by contradiction, which is the opposite way around. Okay, so you won't ever be using contradiction for this. We'll only be using our assumptions. So we want to assume that the probability of k is true, or as we said, we're saying the proposition is true for n is equal to k. K being any number in the natural numbers, okay? So if we were to fill in any random number, we are going to say that it's true. We don't know what it is, but we're going to call it k. We can't call it n because n is our unknown value or a variable, so we're just thinking of another number. That number is going to be k. Okay, so I'm just going to move this up a small bit. Okay, so what we're doing then is, before we were filling in the last part here and the right hand side here, so we're going to take the whole thing this time, and wherever we see n, we're going to put k in instead. So we've got proposition of k is 4 plus 8 plus 12 plus ... plus 4. So it was n and now it's k equals, and the n's here we're going to put in k, so 2k bracket k plus 1. Okay, and we're going to say that pk is assumed true. So we're assuming it's true, so we can move on to the next part. So it's assumed is assumed true, I suppose, yeah. Okay, so 2 is making this assumption. So if I want to say, for each part you have to write the sentences to get the marks as well. So it's well and good writing this and this part here, but you have to make this statement and this statement up here. Otherwise your calculations won't be effective. So it's like, do you agree with the statement? Give a reason why. So this part is like your justification, and this is like the do you agree parts. You have to have this in each part. Okay. So step 3 then is kind of, I'll just move this up, is kind of the harder part of the proof. So what we're doing then is, from our assumption, we want to then prove that p bracket k plus 1. So we're taking it a step further. We have the assumption that when you fill in k for n, that it's going to be true. So from that assumption, we're going to prove then that if we have a k plus the next number, k plus 1, that too is going to be true. Okay, so we want to prove that the proposition of k plus 1 is true, or the proposition is true for n is equal to k plus 1, given that it is true for n is k, which is really important. So you cannot do part 3 or step 3, k plus 1 is true, if you haven't made the assumption that k is true. Okay, so it's like saying that proposition of 1 is true and then going to proposition of 2 is true. So we can't go straight from not n is something to 2 and then go back to 1. So it's a bit like here, we can't go straight to k plus 1. We have to assume k is true first before going on to k plus 1. Okay, so we have proved that p, or the proposition of k plus 1 is true, or the proposition is true for n is equal to k plus 1, given that step 2 is assumed true as well. So that part's really important here. I might underline that bit. Given that it is true for n is k. Okay, that's a really important part. Okay, so what we'll do then is we'll have the same as up here. Instead of proposition of k, we have proposition of k plus 1. And we're going to fill in, for everywhere you see n, we're now putting in k plus 1 instead. Okay, oh sorry, go up here. So for everywhere you see the n part, you're filling in k plus 1. Okay, so proposition of k plus 1, so we've got 4 plus 8 plus 12 plus dot 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 plus 4 bracket k plus 1. So that's our left hand side, equals 2 bracket k plus 1. So that k plus 1 went in for this n here. And then we've got this n here plus 1. So when you fill in k plus 1 for n, you have this extra 1 as well. Okay, so it'll be k plus 1 plus 1 down here. So 2 bracket k plus 1 bracket k plus 1 plus that 1 from the start. So I'm going to highlight it green here. That green one is going down after here, so plus 1. So that's where that plus 1 is coming from. Okay. And then we'll just tidy that up a small bit. Okay, so we've got proposition of k plus 1, 4 plus 8 plus 12 plus dot dot dot. So actually what you could do as well is before k plus 1, we actually have 4k, because k plus 1 is the one after 4k. So if we want, we can add 4k and then put that with it. 4 bracket k plus 1, if we want, equals, and then we'll just tidy this up here. So we've 2 bracket k plus 1 bracket k plus 2, and we'll multiply that bit out in a minute. Okay, so we kind of want to tidy this left hand side up a small bit. So what we're going to do is that if we look at step 2 here and we look at step 3 down here, this part, let me see if I can get a highlighter. I want to call it green, sorry, so we have a green pen here. So this part from step 2, this green box, is exactly the same as this part here in step 3. So those two green boxes are exactly the same, and you've got that 4k plus 1 extra. And what we know is this green box equals this, let's say, circle bit here. And what we're going to do down here is replace the box with this circle on the left. Okay, so if we draw an arrow and say replace with right hand side from step 2. Okay, and we'll have, just squash it down here, I'd say, 2k bracket k plus 1, this comes down, plus 4 bracket k plus 1 equals 2 bracket k plus 1 bracket k plus 2. Okay, and we multiply that out and tidy it up, and they should equal each other on the left and the right. Okay, so I'm just going to turn the page, blank page paper. God. Okay, so blank piece of paper, so I'll just put that up the top bit here, so you can see where I'm going. So we multiply this bit out, so 2k bracket k plus 1, we have 2k squared plus 2k, plus 4 bracket k plus 1, so 4k plus 4 equals, multiply this 2 in, 2k plus 2 times k plus 2, and we'll tidy up. So 2k squared plus 6k plus 4 equals 2k squared plus 4k plus 2k plus 4. 2k squared plus 6k plus 4 equals 2k squared plus 6k plus 4. So they equal to each other. So left hand side is equal to right hand side. And that's what we want. So then we make our conclusion that the proposition of k plus 1 is true, having made the assumption, or having assumed, that the proposition of 1 is true. the proposition of K is true, sorry. That was our conclusion for part 3. Okay, I'm going to treat them there. So that was our conclusion. So part 3 or step 3 is usually the longest bit. That's where we gather most of our marks. And then step 4 is the full conclusion. So this part here is the conclusion for step 3, but what we want is a general conclusion. So tidying up 1, 2 and 3 together. So what you're saying is proposition of 1 is true. So we're just like reminding everyone what we did in part 1. Then we're saying if PK or proposition K is true, so reminding people about step 2, then the proposition of K plus 1 is true. So we're just reminding them of what we just did 2 seconds ago. And then we're going by induction or by proof of induction up to you. Proposition of N is true for all N element of N. Okay, so we're saying it's kind of step 1 here, I suppose. So this is our conclusion for step 1. This is our conclusion for 2 and 3 together. And then this is our, well, look, it's all done here. That's my final. So I'm just going back to the very start of the question, this bit up here. And we're just repeating that and saying done. Okay. So by induction or by proof of induction, proposition for N is true for all for all numbers that are N an element of a natural number. So that's our first type of proof involving series.